going to talk about electric field. Many common forces might be referred to as contact forces, such as your hands pushing or pulling a cart or tennis racket hitting a tennis ball. These are contact forces. But on contrast, we have gravitational force and electro forces or even magnetic forces that act over a distance. There's a force between two objects even when objects are not touching. If you realize that the earth is attracting an object towards itself, even if there is no contact. So those are field forces. The idea of a force acting at a distance was very difficult one for early thinkers. Newton himself felt uneasy when with this idea when he published his law of universal gravitation. A helpful way to look at the situations uses the idea of the field. So basically we say there's a gravitational field, and as the field, if there is a charge, for example, electrostatic field or electric field, if there's a charge there are too many charges surrounded. So if we consider this to be full of charges, and on the corner is a very, very, very tiny charge q, that the effect of this is so tiny that it does not cause any kind of effect on the other charges that are residing in this area. So these charges create a net electric field, because of which there is a force experienced by this tiny charge. So the way we describe this is we say that we can, in principle, investigate the electric field surrounding a charge or group of charges by measuring the force that a very small positive test charge, which is at rest, experiences. By a test charge, we mean a charge so small that the force it exerts does not significantly affect the charges that create the field. So if a tiny positive test charge q, for example, is placed at various locations in the vicinity of a single charge q, where charge q, we can say the charge q is the massive big charge, and it creates an electric field, or it creates a field around it. And if I put the charge somewhere here, say here, and this small tiny charge will experience and some kind of effect due to this big charge. So I could move it to several places, maybe over here, and this charge will experience different forces at different distances. So as it goes farther away, the distance is a key. So once it moves farther and farther away, the test charge is moved away, the electric field will diminish until the unit positive charge will not experience any influence. The way we define electric field is that it is given by the formula of force experienced by the unit positive charge at a certain distance, and we write it as F over Q. So basically, if I have this plus q charge, and if I brought it over here, then it will experience a force in this direction. And if the unit test positive charge is brought over here, it will experience a force in this direction. And if it's taken over here, if the unit test positive charge is taken to location B, it will experience a force FB in this direction, and so on and so forth. So force exerted by plus q charge on a small test charge q placed at different locations. So, and the E, the SI unit of E, therefore, is defined or given by, if E is F vector over Q, the unit of force is Newton and the unit of charge is Coulomb. So the SI unit of electric field is Newton per Coulomb. And there's other way of representing this electric field. If E is equivalent to F over Q, but F is the force between this charge, we can charge and the big charge, the unit positive charge, and the this massive big Q charge. So can we use, instead of this F, we could use the Coulomb's law here, that is Coulomb's law of attraction or repulsion, depending upon what our equation gives us. So this is the magnitude of Q, this is the magnitude of capital Q, small q, divided by R square and Q. If you notice, this small test charge being insignificant cancels in this process, and we get K times Q over R square. So this is the electric field due to experienced by a point charge at a certain distance away from the source charge. So we call it as a single point charge. Apart from that, we also this equation can also be used to find the electric force if electric field is given and the test charge is given. So if E is equivalent to F vector over Q, we can also find F by multiplying Q throughout on both sides. E vector multiplied by Q, where Q is a scalar but electric field and forces are vectors. So this equation can be used in multiple ways for finding electric field or even finding electric force. So here we have a diagram on the side which just represents the electric field at a given point in space. So maybe here where the test charge is, and force on a positive charge at that point is represented by if it's a positive charge, it experiences a force in the same direction as electric field. And if it's a negative charge, it experiences a force in a direction opposite to that of the electric field. For a negative charge, force on a negative charge at that point will be given in a direction opposite to that of the electric field. The electric field is, due to a unit positive charge, is always away from the charge. It may be a good idea to solve maybe an example problem for electric field concept. So we could use the if we have we can calculate the strength and direction of electric field E due to a point charge which is 2 nanocoulombs. Nano is 10 raised to minus 9 at a distance of 5 meters from the charge. So if you have a tiny charge Q and there is a source charge capital Q at a distance R is equal to 5.00 meters. What is the electric field experienced by this small tiny charge at a distance R? We have two formulas for electric field. One is force over Q, or we can also use electric field is K Q over R square, which is actually the magnitude of the electric field is given by single point charge KQ over R square. So we can simply go ahead and substitute the values for K, Q, and R square. K, we already know that K is 9.0 cross 10 to the power of 9 Newton meter square, Coulomb square. So your E will come out to be 9.0 cross 10 raised power 10 to the power of 9. And Q is given as, so there's a 2 nanocoulomb charge, and calculate the strength and direction of electric field due to a point charge of 2 nanocoulombs at a distance 5 meters from the charge. So the test charge, the charge that we are talking about here, is a unit positive test charge, which if you remember, we know that this gets cancelled due to the Coulomb's law. So we are left with the source charge, which is the point charge, over R square. So KQ over R square. So it's 2.00 cross 10 to the power of minus 9 coulombs divided by a distance of 5 meters. Actually, it is 5 millimeters, not 5 meters. So please make a correction here. It is 5 meters will be too large of a distance. So 5 millimeters is 10 to the power of minus 3 meters. So if you go ahead and you have to make sure you are squaring this distance, E will be equivalent to 7.19 cross 10 to the power of 5 newtons per coulomb. That's part A of the problem. And part B is asking you what force does the electric field found in the previous example exert on the point charge. Now we have a very, very small charge, minus 0.250 microcoulombs. So if you go ahead and use the field, the formula E is equivalent to F over Q, F vector will be equivalent to E vector multiplied by Q, or the magnitude of the force will be equivalent to magnitude of the electric field and Q. So the electric field that you created is 7.19. The charges created was 10 raised per 5 newtons per coulomb, and then you go ahead and multiply it with the charge that is given now, minus 0.250 cross 10 to the power of minus 6 coulombs. So the answer comes out to be, you can stop the video here, do the calculations yourselves. This the force is 0.180 newtons. So be careful about the units. It's a force that we are finding, not electric field. So these are the types of problems that will be asked from you to solve for electric field, force, and charge. And this is the formula that we already discussed, how it gets cancelled, and the ultimate formula is E is equal to KQ over R square. By the way, the K value that you see here is actually 1 by 4 pi epsilon naught, where epsilon naught is the permittivity of free space, and it's a constant. So it has a value of 8.85 cross 10 to the power of minus 12. And once we, if we do 1 over 4 pi epsilon naught, and if we calculate that, it comes out to be equivalent to 9.0 cross 10 to the power of 9 Newton meter square, Coulomb square. The actual value is actually 8.99, but we round it for calculation purposes to 9.0. So the force on a point charge in an electric field, we just found that we can also use this equation. And just like we were able to find the superposition of the forces, we should be able to find out the superposition of electric fields as well. So because both are vectors, so if there are many charges and all of them exert a force on a unit positive charge, they should be able to superimpose each other on the other charges, and hence we can combine the forces with the help. We can combine the electric fields by finding the net electric field at that point. So the process is very similar to that of the that you found for the forces that we use. Like you found the charges Q1, Q2, and Q3. And you found the force exerted by Q1 on Q2 or Q1 on Q3. And similarly, we can find out the electric field experienced by 2 due to 1, and electric field due to 3, electric field due to 2, and we can find out the net electric field by using the superposition principle that we are aware of. We could actually use an example. For example, if we have a charge, say for example there is Q charge minus 3.0 cross 10 raised per minus 6 coulomb, and there's a point P where I want to feel or experience the force. Okay, the distance between this this charge minus 3, which I call Q, is 30 centimeters. Okay, and then there is one more charge. So let's say this is a positive charge now. Q is plus. Over here the charge is negative. It is positive charge and same magnitude, but it's positive, 10 to the power of minus 6 coulombs. And at this point P, again same distance of 30 centimeters, we are going to find that the electric field at point P is actually directed towards the negative charge, and the electric field is directed away from the charge Q. So electric field lines, we have a way of representing them. the electric field always points away from the positive charge, and electric field always points towards the negative charge. So the directions are shown like that. So if you have to find out the electric field at this point, you will definitely do E is equal to K Q over R square, and you will notice that you will get a 3.0 cross 10 raised power 5 Newton per Coulomb electric field pointing away from the Q, and over here you will get 3.0 cross 10 to the power of 5 Newton per Coulomb pointing towards the charge because it's a negative charge. So you will have to keep this in mind when we are talking about examples and all. So next, how do we solve the problems for electric fields in electrostatics? And we draw a diagram, show all the charges with signs and electric fields and forces with directions. We calculate forces using Coulomb's law. We add all forces vectorially to get the results. And then we can also find out the electric E fields. Because E is equal to F over Q. So if there are many charges, then we'll have to find F1, F2, F3, and then find the electric field experienced by test charge at a certain location. So we will also be able to find electric fields. The problems that we solve here are going to be basically very simple. So this is from your Giancoli textbook. The electric field needs to be found here. A proton is released in a uniform electric field, and it experiences an electric force of 1.86 cross 10 raised per minus 14 Newton towards the south. So if there is a uniform electric field, now how are uniform electric fields are created in a special way? So for example, if I have a positively charged electrode and a negatively charged electrode, this creates a uniform electric field. See, the electric field lines are pointing away from the negative but pointing towards the negative, but away from the positively charged plate. But the field is uniform. This is what we are trying to tell you. Within this straight two parallel conductors, the field is uniform, and it experiences an electric force of the force that this charge, the proton P, it will experience a force towards the negative charge, but it will experience repulsion due to this positive plate, but it will get attracted to the negative plate. You could also draw this diagram like this. I have a positive plate or a negative plate. The electric field could have been shown like this. So there are different ways that you can show this uniform field. Okay, so the direction of arrows is the E field here. Or if you could keep this negative and this one as positive, then your direction of the arrows would change. You would have to draw the arrows in the opposite direction. And if the electric field is directed this way, the force on the charge will be experienced in an opposite direction. So that's why towards the south. Find the magnitude and direction of the electric field. So your E is basically given by force experienced by the test charge, and we have a proton. The charge that we have is proton, so we know the charge of the proton as 1.6 cross 10 to the power of minus 19 coulombs. So we'll go ahead and use that. So your E vector is F is given to us 1.86 cross 10 to the power of minus 14 north south newtons southwards. So you don't have to actually think about these diagrams, just keep in mind it is southwards. and divided by the charge 1.6 cross 10 to the power of minus 19 coulombs. If you work on it, the electric field created is given by 1.16 cross 10 to the power of 5 newtons per coulomb south. Okay, so because my plates are in this way, the electric force will also be in this direction. For me it is north, but if you swap the plates, you can say either north or south. So the next problem we work on is a downward electric force of 6.4 Newton is exerted on a minus 7.3 microcoulomb charge. Find the magnitude and direction of electric field at this position. So pause the video and go ahead and find out the electric field. So electric field, again, the formula is force per unit charge, which is equivalent to 6.4 newtons downwards and minus 7.3 cross 10 to the power of minus 6 coulombs. So it's a negative charge. Minus 7.3 is a negative charge. So if the electric field is downwards, the force must be in the, if the force is downwards, the electric field must be in the opposite direction. So if the force is downwards, the electric field will be in the opposite direction because it's a negative charge. And while as in this scenario it is a proton is positively charged, so that's why the direction of the electric field and the electric force are in the same direction. So yes, so if you find the electric field first, let's find the magnitude. It's 8.8 cross 10 to the power of 5 newtons per coulomb. If the force was down, the electric field will be up because the charge under consideration is negative. So if we go back few slides, we talked about if the unit positive charge is Q, the direction of electric field and force are in the same direction. If the charge is negative, the direction of electric field and force are opposite. And similarly, we can work on another problem, which is, these are pretty simple problems. Assuming that you have an electric field strength at a point in space where a proton experiences an acceleration of 2.4 million Gs. 2.4 million Gs means the acceleration is given as 2.4 cross 10 raised power 6 times the acceleration due to gravity, which is 9.80 meters per second square. So this is just to add a little bit of surprise element to it. Basically is telling you acceleration is given as 2.46 cross 10 raised power 6 times the acceleration due to gravity. So you have to find the electric field. So we know that Newton gave us the force as F net is equal to mass times acceleration. And in an electric field, if there's a charge, there's an electric field created. The force can be readily given by F over Q. That means F is equal to E times Q. So instead of writing, the only force that is acting here is due to the proton, which is in the space, and so it's E times Q, which is mass times acceleration. And we can easily find the electric field by rearranging the terms and working on the numbers. So we know the acceleration be the mass of the proton, because it's a proton that it's 1.67 cross 10 to the power of minus 27 kgs. And charge on the electron is positive 1.6, 10 to the power of minus 19 coulombs. So we have everything now to go ahead and work on this. So substitute the values and show the work. So your proton is 1.67, 10 to the power of minus 27 kgs, multiplied by acceleration, which is 2.4 cross 10 to the power of 6, 2.4 million, times 9.80 meters per second square, divided by the charge, which is 1.6 cross 10 to the power of minus 19 coulombs. Go ahead and solve it to find the electric field. You can pause the video and work on the numbers, punch in the numbers properly, following the PEMDAS, and solve for this. So you get 0.2456, which can be rounded to 0.25 newtons per coulomb. We can work on another problem. Now this time we have an electron that is released from rest in a uniform electric field, and it accelerates to the north at a rate of 105, at the rate of 105 meters per second square. Find the magnitude and direction of the electric field. So this is an electron now that is released from rest. We do the same thing in this scenario also. Net force is mass times acceleration, and the net force is basically charge. Again, electric field is force per unit charge, therefore not the magnitude, sorry, force is Q times E vector. So instead of writing the net forces, here is Q times E, which is force, is equal to mass times acceleration, and this time it's the mass of the electron. Mass of the electron is 9.11 cross 10 to the power of minus 31 kgs, and charge on the electron stays the same. If you're not putting the magnitude, then you should put 1.6, because we need to find the direction, so negative sign is important. So your E vector is equal to m into A over Q. Go ahead and substitute the values. 9.11, 10 to the power of minus 31 kgs. Acceleration is 105 meters per second square north. So, and divided by the charge, minus 1.6 cross 10 to the power of minus 19 coulombs. If the force is towards north, but this is a negative charge, so you can understand the electric field found in this scenario, which has a magnitude of 5.97 cross 10 raised power minus 10, if you're doing the math correctly, Newton per coulomb southwards, because we know that it works in a direction opposite. If it's a negative charge, the electric field is in a direction, electric field works in a direction opposite to that of the force. The next one we work on is problem number 32. It's a good problem based on superposition of electric fields. So just like we talked about, forces can be superimposed, hence electric fields can also be superimposed. So for two point charges, minus 32 microcoulombs and plus 45 microcoulombs are separated by a 12 centimeter distance, and the electric field at point P, which is somewhere far away from these. So we have to find out what P is experiencing due to Q1, what electric field is experienced by P due to Q1, and what it's experiencing due to Q2. So we don't know the distance x, so we have to find out the electric field at point P. we say it is 0, that means it's balancing. That means the electric field created by Q1 and electric field created by Q2 must be equal and opposite to each other, and hence they balance out. So that's the key information. So how far from Q1 is P? So your job in this problem is to use superposition principle to find the distance x. So there's only one scenario when the electric field due to the E1 and E2 at P will be 0 if they come out to be like this, which therefore means magnitude of the electric field E1 must be equivalent to magnitude of electric field E2. This is the electric field that is experienced at P due to charge Q1, and this is the electric field experienced at P due to charge 2. So we first find E1 and E2. So E1 will be equivalent to K times magnitude. We're going to find the magnitude of the charges and then give the directions to it. The K times Q1 over R squared. So R square is basically your 12 centimeters, but you want to put it as let's put it as L right now. Let the distance between Q1 and Q2 that is shown here be L. So we'll name it as L square. Actually, we don't find the distance between the Q1 and Q2, but if this is X and this is L, so we can name this as X plus L square. Sorry, we're doing Q1, so it is X square. Okay. And for E2, we can go ahead and write it as K times magnitude of charge Q2 over, now we are talking about Q2 from P point, it will be X plus L. We'll substitute the values later so that it's easier to solve. And now we set them equal to each other. K times Q1 over X square must be equivalent to K times Q2. These are the magnitudes, so whole divided by X plus L whole square. The K and K will cancel, so you will have Q1 times X plus L whole square equivalent to X square times Q2. We will have to work on this equation, which is X square plus L square plus 2XL is equivalent to Q2X square. So we'll open this. This will be Q1 X square plus Q1 L square plus 2 Q1 XL is equivalent to Q2 X square. So it's kind of going to be a bit complicated and in quadratic form. So if you work on this equation, or maybe if we could have simplified it, but it seems it's difficult to simplify it this way. But we know we have, let's take a look at it. We have Q1 X square plus minus Q2 X square. We'll combine the X squares together, minus Q2 X square plus Q1 L square plus 2 times Q1 XL equivalent to 0. Let's rewrite the whole equation. Q1 X square minus Q2 X square plus Q1 L square, which is a constant, plus 2 equivalent to 0. So we can take the X square common. We'll have Q1 minus Q2 plus 2 times Q1 L and X and plus Q1 L square. So the two charges are, we know the two charges. we know Q1, we know L. It's going to be a quadratic equation in X. This is going to be the constant term. So this may take a little bit of manipulation. Once you're done with the work, you'll get two values. So the ideal one, the X position is X is equal to 64.57 centimeters once you work on quadratic equation for X, which is minus B. Obviously, this whole thing is your B. This is going to be your A quadratic. This is the coefficient for the quadratic, and this is all of this is C. So once you substitute values in this and work on the quadratic equation, you'll end up getting X is equal to 64.57, or we round it to 65 centimeters, or round it to 0.65 meters. So it's a good way of getting a practice for the quadratic. So we know what is Q1. Q1 is your minus. If you remember, we are taking the magnitude, so don't put minus, only use the magnitude of Q1. Okay, Q1 as just the magnitude. We talked about here, we are using the magnitudes here. So everywhere we're using magnitudes, so use Q1 as 32 microcoulombs and use Q2 as 45 microcoulombs. Your L is known as 24 centimeters. You can keep it in centimeters. 12 centimeters. And the only other term that we don't know is X. That's what we are finding. Okay.